Good afternoon, ladies and gentlemen. We are happy to have Johannes speaker. Johannes Zimmer as a speaker. Sorry. So Johannes got his PhD in 2020 from the Technical University of Munich, and then he went for more than 3 years to Caltech, to the group of Kaushik Bhattacharya. Afterwards, he was a emeritus postdoctoral fellow at the Max Planck Institute for Mathematics and the Sciences in Leipzig. And afterwards, he got a position at the University of Bath in the UK. Then he started as a lecturer, but finished as a full professor. And from 2020, he is full professor at the Technical University in Munich. And today he will speak about generic system derived from the Hamiltonian.
Thank you very much, Martin, for the invitation. Thank you very much to all of you for coming. And it's always nice to be in Prague, which is such a rich place and so excellent. And so I learned many things in the discussion I've had here over the years with many people. So it's wonderful to be here. I see that for some reason the last line here didn't show up. I should say this is joint work with Alex Mielke and Marc Pelletier. It will come in the very last slide. It's a long project with Alex Mielke from Lias and Marc Pelletier from Eindhoven. And finally, we understood something I want to present today. The title might look strange for people who don't know what generic is. I'm going to explain that. But before we come to this, first, this is a picture you've seen probably often in many different disguises, but this is also the context of this talk. So there are the different scales in space and time. So here's the spatial scale and the time scale. And this is the picture I have in mind as Hamiltonian model. So there are atoms interacting by simply Newton's equation of motion. So there's a Hamiltonian system, very high dimensional. So ideally 10 to the 23 atoms. And then there are different ways of coarse training, but then to compute efficiently, you would like to have descriptions in terms of continuum mechanics, so also thermodynamics. And the question is, how can we go from this scale to the continuum? And I'm going to discuss this in a very simple example, where we could do the analysis rigorously to explain what the core difficulty is. We can think about the following. I give you 2 movies of the same system. Once I show you a movie of all the atoms moving somewhere, say in a fluid. And then I show you a movie of the macroscopic description. And then I ask you at the end of the movie, did I show the movie to you in the correct way, or was I playing it backwards? For the Hamiltonian picture, you have no way of answering the question correctly. You have to guess, yes? But Newton's equation of motion are invariant under time revolution. Of course, continuum mechanical equations are typically irreversible. You can't reverse them under time. So philosophically, one of the questions we would like to understand is, how does this macroscopic irreversibility appear? Or in more popular questions are, how do we get the error of time? That here on the continuum, I can clearly say in which way is time evolving. And so there are 2 systems. I want to go from a microscopic model to a macroscopic one. The microscopic one is a Hamiltonian model. So think, for example, of a molecule, like here this molecule immersed in many particles of a solvent like water. So very high dimensional, Hamiltonian, and time reversible. That's really important since we usually have a Hamiltonian system and we want it to be deterministic as much as possible. We will later on believe that the heat bath, so the red particles that are the solvent, will have random initial data. Otherwise, it's a deterministic system, and then we would like to get a macroscopic description, so-called generic. I'll explain it on the next slide. And typically what the system will show is it will show some effects of irreversibility. There will be dissipation, friction or something. Therefore, the system will be irreversible. So we would like to understand how this error of time appears when we go from the microscopic to the macroscopic model. But first, what is generic? Since that's really the question we started out, so we would like to derive a system not just on the macroscopic scale, but in a very specific form, which is called generic. So generic is a term framed by Hans Christian Oettinger. It stands for General Equation for Non-Equilibrium Reversible Irreversible Coupling. There's a book by him, and there are references at the bottom to work by him and Mela, I think from Prague originally, and Morrison. And what is generic? So generic is an abstract equation of this type. It says I have a state space Y, which is evolving the following way. The time derivative is equal to the sum of two terms. The players are E and energy and S and entropy. It's just kind of thermodynamically naturally. And I take the derivatives of the energy and of the entropy, that's the D, and then I feed them into operators. And the operator I'm feeding the energy E in, or its derivative to be precise, is a symplectic operator. So there are details, the important point is J is a symplectic operator, so it's energy conserving. K, on the other hand, is dissipative, so it's a symmetric operator. K transpose equal to K, and is positive semi-definite. And there are degeneracy conditions. If I feed, so to speak, the wrong argument in an operator, so I feed the entropy in the symplectic operator, I get 0. And if I feed the energy in the dissipative operator, I also get 0. Why do I need this? Well, with this non-degeneracy condition, it's very easy to compute. For example, the energy, how does the energy change? I look at the time derivative. I apply the chain rule. And then I plug in for the time derivative of y, the generic expression. And then I see I get one expression which vanishes by the symplecticity of j. And second, if I look at the second term, dE and k, if I take the k over as adjoint operator, I get kdE, which is 0. So I automatically get that the energy is conserved, and a similar computation shows that the entropy is a Lyapunov function. And so why is this structure interesting to us? Well, first, essentially, all the equations you can think of in continuum mechanics and thermodynamics can be phrased in generic form, with few exceptions. So plasticity in materials with memory need an extension of generic, but you can extend generic that also plasticity is covered. But for example, the Euler equation of Stokes or elasticity, thermoviscoelasticity can all be cast in this framework. A very nice article by Alex Mielke in CMT writes down the generic form for many, many different equations. And I said, one benefit is if I can write something in generic form, I know automatically the system satisfies the laws of thermodynamics. Entropy is monotone. Something we don't understand yet very well is, could one use the generic structure to introduce splitting methods for analysis or discretization for numerical schemes? There are some works on the way. There's something that is published, but it's still very much in the infancy. But what we would like to do is derive the generic form of one system from the microscopic Hamiltonian system. And that is the other justification for generic. One could say, well, why do we need generic? We can check for thermodynamic consistency in different ways. Philosophically, that's the point Oettinger says. You have some system, physical system, you coarse grain then you get a generic system. If you take a generic system, you coarse, then you get generic. So in a sense, generic is the natural equation, natural form of equation you would expect to see when you coarse. And that is something we wanted to see. In terms of physics, what we do is a little bit related to Moritz-Zwanzig, but it's different. So, well, that's probably easy for many of you, but I wanted to write on one non-trivial generic evolution, which has nothing to do with the equation I'm going to look at later on, but I want to take the simplest possible example, linear diffusion, and I claim this can indeed be written in this generic form where the first term vanishes. Yeah, there was an energy term with an operator J, and that is 0 here. I only get the distributive evolution. And that relates to something which is very popular in mathematical literature. This is formally a gradient flow. And to see that this indeed reveals physics, I take the Boltzmann entropy, rho log rho, integrated with a minus sign. K is in this case the Wasserstein operator, divergent of rho of gradient, also with a minus sign. And then I claim I can indeed write the linear diffusion equation in this way, namely minus diffusion of rho gradient, that's the K, acting on the derivative of ds. Since ds was the variation derivative of the entropy minus log plus 1. So I take the operator, I plug ds in, I get the rho as the prefactor, then differentiating the logarithm is 1 over rho, and then by the chain the gradient. So in total I get the Laplacian since these two rho's cancel. And that also shows one benefit which was important for us in a different relation. You can say, well, okay, one side, of course, this is the famous Wasserstein gradient flow of Felix Otto and Kinderlehrer and Jordan and others. So this has, you can think of generic as an extension which includes conservative evolution. But one benefit is also, you see, what it looks more complicated since it's a nonlinear operator while diffusion is linear. But really what generic is doing is it takes the force, ds, the derivative of the entropy, linearly. And it gives me a velocity, which also appears linearly. So these are two equations, so the ds appears linearly and the velocity appears linearly. Now back to the problem. This is a slide I've shown before. I've only added 2 lines, I think. So I want to go from this Hamiltonian system I introduced before, which is time reversible. And now it will be important that we phrase this in the correct mathematical language. And I say, okay, since it's time reversible, this high dimensional system, in fact, it will be infinite dimensional, is given by a unitary group. Okay, so the unitary group describes the evolution of the microscopic system. The generic system is typically, if k is non-zero, dissipative. So it is irreversible. Now, how would I describe the macroscopic evolution of something dissipative? Well, it is a contraction symmetry. And you see already the arrow of time appearing. You have a group in the microscopic system. You can go in both directions. Macroscopically, you only have a semigroup. You can only march forward in time. You can't go backwards. And contraction means the norm of the semigroup describing evolution will be less or equal than 1 comes later. But that is the core point. So kind of for us, it says what seems to be what we are going to exploit is with a unitary group, and then we somehow want to coarse grain, and I'll explain why and how, and then we get something dissipative, we get a contraction semigroup. How does this work? And there's a beautiful mathematical theory behind, and that is the theory of unitary dilations, which is probably something at least many of you haven't seen. So I want to explain the theory, and then I'll do an example. So what are these unitary dilations? They do the opposite of what we want. So we are in a Hilbert space, and we have a semigroup of contractions. So which I take in this way, yeah. There's a contraction, so as I said, normal less equal than 1. And think of this as being something dissipative. Yeah? Think of this as the generic system we want to derive. Yeah, it's a dissipative semigroup. And then I can take the system, I can embed it in a space which is larger, this space X, is comprising my original space. And on this larger space, there's always a unitary group, which for the purpose of this slide, I write in this way, such that the following is true. If I first project on the small space Y, then I let the unitary group run. Typically, it will leave the space, the small space. But if I project back, then I get my original semigroup. And that's a beautiful theory is of PISA orthogonal projection. P will appear often. That's a theory going back to Snagi, Bela, and Boyas, for example. So there are a number of works in this area. And so in terms of modeling, the idea is this could be exactly the opposite of what we want. Yeah, since we have here we have a start with a small space and we embed it into a bigger. So is really what the coarse training is doing the opposite. We start with a unitary group, and then we project on a semigroup. And the answer will be yes, and that is what we, well, as well, of course, call a compression. So the idea is we are given an infinite dimensional Hamiltonian system representing the molecular system. It's a unitary evolution, and then we want to find a compression, a projection on a finite dimensional space that gives us generic. And then we want to learn about generic. So that is what we will have ahead of us as programming. So maybe I go through this with the hand of a simple example. Yeah? So what I really want is, the philosophy is, this is now, well, it's badly arranged. This is the macroscopic picture. This would be the thermodynamic evolution. We have a contraction semigroup, which I write as e to the minus dt in a small space. The theory says us this we can always embed into something which is unitary, is living on a bigger space. In the unitary group, I write it as e to the d there. And we want to do exactly the opposite. So we want to go from the big system, project, and land in a small system. And projection means, well, if I start in the small space, I evolve it with the small group, the distributive group. That's the same as evolving with the unitary group and then projecting. How can this work? Well, the statement about contraction and dilation look miraculous at me. So let's do the simplest possible example of a distributive semigroup. Y dot equal minus COY. Yeah, we all know the answer. It's given by the semigroup e to the minus CT. Okay? And the theorem says I must be able to embed this evolution into a unitary group. And how do we do this? That will be important that we explain the model we are going to use. So I'm trying to find this unitary group which embeds this e to the minus CT semigroup. Such that, again, this projection of the big group deals with the small. How do I do this? One example, one answer is I do the following. I say, okay, my big space is L2 of R. It's a nice space. And on L2 of R, I have a right shift. I take an L2 function, I shift it to the right by some factor CT, okay, or some speed C. So this is a unitary group, but in fact, this will be the embedding of the simple y dot equals minus cy. I had a toy model for something dissipative. This is something I will use several times later on. I take a special class of functions, so it's the exponential on the left half axis, 0 on the right. So this looks technical, but this is something we will really use often. So this is it's an L2 function, yeah, and it's normalized. It is normal. If living in L2, I say I take this one-dimensional space spanned by this one function, and I have a projection from L2 onto this function space. And then I want to see what happens if I take W, I apply the unitary group to it, which is right shift, and then I project. Well, the unitary group is shifting to the right, and then the projection is the inner product of L2 with W. And if one does the calculation, one gets that it's e to the minus CTW. And here you see the dissipation, yeah? This is the dissipation that has appeared. So what you can think of is I'm moving the entire object, the entire function, it's unitary, but I'm projecting effectively on the left half plane. So I'm losing everything, all the information that has traveled to the right half plane. So the entire object W move with the unitary group still has all the information, but since I am projecting effectively to the left half plane, I lose information and I become dissipative. That's the core idea. And for a long time, we were not sure which model to try. We tried several ones. It was really this example that told us what a good way to go about it. Namely, this is an example of a dilation, and in fact, one can show minimal dilation are unique up to isomorphism. Therefore, what I've shown here is actually, in a sense, a very general thing. The right thing is a completely natural choice. That if I want to write this as a unitary group, it's e to the jt. J is minus c times the derivative, and the Hamiltonian is simply normal beta squared. And that is what we're going to use. So why is this relevant? So if I compute, I mean, this minus c says the time derivative gives a minus c in comparison to the space derivative. So that's the way of encoding the unitary shift as the right unitary operator. And when we compute that, the Hamiltonian is then simply the L2 norm. And in a sense, this is really the natural thing. It's up to isomorphism, the only minimal dilation in this case. So we will take this Hamiltonian for the system. So this is finally the model, but it was important for us to understand how we got the model. So the previous slide is taking us 5 years to understand. Once we got there, everything was much easier. So the model is quite simple. We say, okay, we have a finite dimensional model system. This is called system A. Think of a molecule, a heavy molecule living in a heat bath. Yeah, so the system A is a Hamiltonian model for the Newton's equation of motion. This has a space Z. It has a Hamiltonian depending on A, and it has a symplectic structure J. Okay. And then I do exactly the same thing as in the picture with the red water molecules. I couple it to a heat bath. And the heat bath is really inspired by the previous slide. So it's an infinite dimensional space. It should be energy conserving. So there's a Hamiltonian and a symplectic structure. And these two I couple, and the coupling is in a linear way. So I think I've said most of these things here. Yeah. So yeah, when the coupling is that. Again, in terms of what we want to do is that we have this huge system. This is in some Rn. This lives in a infinite dimensional Hilbert space. These are coupled. So my big system, my microscopic system is living in Z cross times H. Yeah? In this infinite dimensional system, unitary, now I want to compress to a generic system. That's the idea of what we want to do. Trouble is, we don't know which space to compress it to. So how do we go about that? Okay, so first, Okay, what is the Hamiltonian? There's not a lot of content here. It's again the same system. So Z is the heat bath variable. And okay, so H, maybe I should call this H is for heat bath, but also you can think of this as a capital eta. And the variable eta, the variable in the heat bath we call eta. So heat bath variable eta is coupled to molecule variable Z with a linear coupling operator Z. C. So C is kind of mapping the molecule into the inverse space. So we have a relatively arbitrary Hamiltonian for the molecule. With the heat bath, it's exactly in the example before. We take as the L2 norm, exactly as it was in the case of the right shift. Then we have the linear coupling. Yeah, that's kind of the system we settled for eventually. It's kind of a secondary exercise to write down the equation of motion, with the Hamiltonians acting on the derivative and the variable appear here. That's a system in an infinite dimensional space, Z times H. And the point is, the benefit is the heat bath is a linear equation. That is something we will use. So, first, this is the, oops. Sorry. Sorry? Thank you. So we have the equation of motion. This is an infinite dimensional system. So of course, the question is, does the system have a solution? Yes, under mild assumptions on the growth of the Hamiltonian, it does. So how would a physicist go if I gave this equation, the system equation to a physicist would do the following. He or she would solve the second equation using Johannes principle and plug it into the first equation. So we try to do this, we write down the solution to the second equation with Johannes principle. Yeah, that's this equation here. Well defined, so I can make sense of it. It's, one thing we will need later on, necessarily, we say this initial data is now random. We need to introduce some randomness, which will define a stochastic process. So we need that the initial data of the heat bath is random. Everything else is deterministic. So this is what a physicist would do. And then in the more expansive approach, they would apply projections. And this is where the trouble starts. If I take this equation and I project to a subspace, typically the subspace will not be invariant. So the equation on a projected subspace is not well defined. So we need to do something, we need to find a well-defined subspace onto which we can project such that the projected evolution is well defined. And this is precisely this idea of contraction. So that's why I introduced the dilations before. We use now the opposite way. We say we assume there is a suitable projection. So we have this high-dimensional system, the microscopic system, infinite dimensional, and we want to find invariant subspaces. And the core assumption is that the reverse of the dilation holds true. Namely, there is a linear operator B on a subspace W of the heat bath, or whatever space we're looking at, Z times H in the end, such that if I take the big group, I look at the corresponding evolution, then I project, I get a distributive group with assumption on the eigenvalues. And we in the example I show you at the end, this will be the case. I show you another example along the way. Assuming that this core step is satisfied, then we can do what physicists would like to do. We take the system from the previous slide and we project. So I introduce a projection here, and the projection, if it commutes with the integral, ends up here in this group, and this expression is, by the contraction assumption, a nice dissipative sine group. And if I then look at this equation, I say, okay, the projection I call W, then I find by integrating by parts that this equation is in fact a mild form of a nice deterministic system plus noise. But the nice system is here, this is a local system. Yeah? This is a system which is a well-defined invariant evolution on the subspace W. Yeah. So let's see how that goes. So with the system, and I'll give you one specific example. I'll show you how this construction works. And it's essentially the same I've shown before. So the system A, fairly general, it's a Hamiltonian to describe a molecule. Let's say it's a position in the momentum. So it's the kinetic energy, the potential energy, and the usual symplectic structure. Okay, nothing surprising. The heat bath, given that I've shown you the example before, is also exactly the same. Yes, it's still two functions. I have the quadratic Hamiltonian as I have for the right shift, and I have the symplectic structure exactly of the right shift. Yeah, and now only now it is in 3 dimensions. So in particular, this is really the vectorial version of the right shift. The only point is that the coupling involves only the position, not the momentum variant. So one can write down the equation of motion. It's not important, but what is it structurally? It's an ODE in Q and P coupled to a PDE in beta. But one can make sense of this in a rigorous mathematical way. So how does the compression in this case really work to show that the compression assumption is not empty? This looks horrible, but I'll try to walk you through and convince you, in fact, it is really what you've essentially seen before. I choose 3 functions. I want to project this infinite dimensional system on a 3-dimensional space. So I want to have a dissipative operator D on R3 with one real eigenvalue, positive, and two complex conjugate eigenvalues, where I also see 2 is positive. So I define in this L2 space 3 functions. Well, this is just a vector with the component 1. Then here with e to the C1, I do exactly the same as before. I have the exponent on the left. I'm cutting it off on the right with the chi, that's the indicator function of the left half plane. And I do essentially the same, but now I also to deal with complex eigenvalues, this will play a role later on. I get 2 more functions. So I had 1 before. Now I have a compression subspace consisting of 3 functions. I define the orthogonal projection on this space, and due to the green terms, these functions are an orthonormal basis. And then I claim that in this case the compression assumption holds. Yeah, so I evolve a big group with a linear combination of these functions, and then I project. And normally I would leave the space I would like to live in, but in this case I claim no, I don't. I really get a nice dissipative evolution. Why? Well, first to understand that it's quite non-trivial. I take one of those functions, one of those 3. I evolve it forward by a shift, yeah. So this would be the unitary group. Well, if I take such a function, I shift it, immediately I leave the span, yeah. So the evolution immediately leaves the space W. But then I project using the indicator function, which is element of the projection. So if I then project again in the left half space, I'm again in my function space. So in that sense, I get a well-defined evolution. So the core is the projections here, essentially projecting on the left half plane. And then one can compute the projected operator B, which is the dissipative one. And one can see that indeed the compression assumption holds. That if I evolve the big group and then project, that's the same as having a small low dimensional, in this case 3-dimensional dissipative Zimmer. So this is in principle the structure that gives us generic. And so to be a bit more precise, so how do we now go from the unitary group to the dissipative group? How do we go from microscopic to macroscopic? We define a map, a force-graining map. It takes the two elements in my system, my molecular variable and the heat bath variable. The heat bath I project in the center of contraction. And also, that's a feature of generic, I introduce a variable E, energy density, which measures the energy, which measures the exchange of energy between the full heat bath and what is feeding into the finite dimensional system. So I'm going from this big space to a small space. The small space is the same. The heat bath becomes now a low-dimensional object, could be one-dimensional, and then I have the energy E. And using the theory of contraction and dilations, now exactly we see what we want, namely we get a closed system in Z and W. And that's different from what many physicists would do. So physicists would try a projection, maybe in this variable, Z, and then they get an equation which is not closed, non-Markovian evolution. Then they try to introduce an additional variable, which in this case would be W, such that the evolution becomes closed. So when in hindsight, of course, we get the same thing when we get it with this approach, but here it comes out as nice, and structurally there has to be this W coming out of an invariant subspace. And this equation can be put in generic form. I'll show that at the end. So in a sense, we could say mission accomplished. We had this high-dimensional macroscopic system. It was reversible since it was unitary. And we projected, and the projection, like the shift of this frankly defined in a half space, a loss of information. This loss of information makes it time irreversible. And one can write down an energy and so on. So I could say mission accomplished, but it feels a little bit unsatisfactory since we haven't really understood why generic looks the way it does. So we get one equation, it's not in generic form, and then we put it in generic form in hindsight. That's possible, but it's a little bit unsatisfactory. So to explain, okay, but this is kind of what we have done so far. So that's kind of, we have this coupled system. We get this projected variable, which has a nice evolution equation, and then we get a low-dimensional macroscopic system. And I'll write down the equation at the end. But it's not, to me, not satisfactory if we don't understand really why does generic the way it look. Why does, for example, K have the structure it will have in the end? And that's why I haven't shown you the equations yet. To understand that, we need the situation where we don't have deterministic initial data, but we now really use crucially the fact that we can run the system with random initial data. And then we can learn more than we can do in a deterministic case. And I think in the interest of time, we skip this slide and I say one can make sense of a stochastic process on this big space. And it's called Hamiltonian theory. I'm going to skip this, yeah? So it's a non-trivial question. How do I define a Gaussian on the infinite dimensional space? Answer is Hamiltonian. Let's forget that. Let's try to live with the gist. So I start, I only look at the heat bath, but I'm running out of time, am I?
Not that you can still go for maybe 15 minutes.
Okay, good then. Okay. For the moment, I do it only for the heat bath. Because I can help it. It can be a bit slower. So I have the heat bath. Exactly like the right shift on the real axis, where the functions are only non-zero in the left-hand side. So I have the quadratic Hamiltonian, I have the symplectic structure, which was a minus dx. So, and here I have a well-defined evolution. Then I need to do something, and this is what I skipped on the previous slide, to go to positive temperature in a bigger space. And that gives still a well-defined evolution, now with a different semi-group S hat, which I can't write in this way, but it's a this is a well-defined evolution. And then I project, and the contraction says, okay, there's one interesting part, this one, which gives me really the noisy, it gives me the deterministic system e to the minus ED, that's the contraction semi-group, that is the dissipation. Okay, what happens with the rest? So I look at the orthogonal complement, what happens with the part of the initial data which is not projected? I feed that into the semi-group, I project, and then I get this expression here. I get a noisy system. Yeah? So what is this? This is saying the projected process is evolving according to one deterministic evolution here, and then there's a stochastic process. So DBS is a Brownian process with various sigma, and then there's a time integral as we see before. So that's the weak form is simply an onset Wilbeck process. Yeah, it's a first order Langevin equation if you. Yeah, so we can rigorously derive for the heat bath this onset Wilbeck process. And therefore, this sigma will play a particular role. And now that what the full picture is really now, I do exactly the same. I only introduce the coupling to the molecule. That doesn't change very much. Basic picture is here for the heat bath. I get one deterministic evolution, which gives me my additional variable, and the rest gives me an Ornstein-Uhlenbeck process. What's the outcome? Now I can write on the generic form, and now it has an interpretation, unlike it is in the previous situation. So first, what are the variables? There's Z, the value of my molecule. W, that's the projection of the heat bath. That's what comes out of the contraction assumption. I take a heat bath variable eta, I project, then I get a W. And then there's the energy E, which we carry through the system. How does it evolve? And now I say, okay, here now I can write down the evolution. So first, this is the generic system. That is what I have on my second slide. Here comes a term I had forgotten. No, I haven't forgotten. It was missing there. But now comes sigma times noise. And this is the stochastic version of generic. So if I take a deterministic generic, which is this part, I add noise, then also this term has to appear. So it's not hugely relevant. But you see kind of, you see that's, well, there's one insight which is helping us. As soon as sigma appears, K appears. So if sigma is 0, I get only the deterministic part. As soon as I switch on sigma, I get K here. So clearly the sigma I derive, the noise prefactor, has something to do with K. And how does it go? Well, the energy is not very surprising. It's the Hamiltonian of the molecule. It's the energy on my projected variable W. It's the coupling. And it is the energy which is kind of what I was exchanging between the heat bath and the system. The entropy looks a little bit funny, but it is also proportional to the energy E. And then one can compute the operators J and K, and this is now some structure appears. Yeah? So that's why I was doing this three-dimensional example before, the three functions I was protecting. So J has a symplectic part in it, not a surprise. From the projection D, it has the skew-symmetric part. Yeah, so if D has is not symmetric, but has a skew-symmetric part. The skew-symmetric parts define the conservative evolution. And K is messier here. The point is that in K, the symmetric part enters. Yeah, so the symmetric part of D enters here, and the skew-symmetric part enters in J. So, yeah, again, why the energy? So the energy is measuring how is the exchange of energy between the system A and system B. So how is the energy between Z and the reduced variable W? And that is what I had before. It's the interaction, it is the projected L2 energy for W. Projected meaning is a value for W, and is the Hamiltonian of the original molecule. So this is a natural Hamiltonian. If I compute the trade-off change of E, transport of adjoint is up to a factor of 2 identical to K. So the noisy data allows us to identify sigma, and if we know sigma, we know K. And also there's a way of deriving what the entropy is. So we can, in the stochastic case, rigorously derive the dissipative part. So we have good reason to say why do the dissipative parts the way they do. One is there's this fluctuation dissipation statement, and second, the entropy can also be defined in a way which physicists would find very natural. And then everything else goes in the symplectic operator and the energy, and that's not completely clear how this can be split. I mean, we can write down the decomposition with a natural energy, but there's something we don't quite understand how this part splits. But bottom line, the stochasticity was important since it allows us then to understand why the dissipative operator K appears. And as I said before, so the projected semigroup, the dissipative group, if I split it in symmetric and skew, then the skew part enters in generic the symplectic operator, and the symmetric part enters the dissipative operator. It's not unsurprising, yeah, you would expect this. J is symplectic, so it should involve the skew part, but it is not completely clear how this goes out. Now the algebra works so nicely. And yeah, I think this is what I wanted to say. Yeah, the J I have already discussed. There are some parts, some technical aspects, I think I have been quite technical. There are various aspects I have not covered since the total paper are 50 pages. So there are many aspects I haven't discussed since already trying to explain the ideas was relatively technical. There's more we learned along the way. So here's now finally with the name of the co-authors. So Alex Mielke from Biotrust and Mark Retier from Eindhoven, and it's something we've put on archive relatively recently. I should say it's a very simple system we are doing. Yeah? We have a finite dimensional system which we couple to a linear heat bath for good reasons. That was why I want to discuss the dilations, but also the coupling is linear. Nature is more complicated. I think nature does nonlinear couplings, for example, and that is something we don't know how to deal with. And I think if one could do this, it would be significant progress, since then we could compute much more efficiently. And kind of part of my dream is that this picture I've shown you twice, solvent in a molecule, is not needed in 20, 40 years or so. And that's really how physicists compute. Yeah? If they want to understand a molecule, they put in thousands of solvents, and then they compute on a supercomputer. So really, a huge percentage of energy in computing time is lost on trying to compute water, since we don't understand the effect water has on the solvent, which we really want to understand. But for this, we would need to understand a picture in this vein, but much more complicated with much more nonlinear couplings, which we don't do. So that remains an open question. And with this, I thank you for your attention.